Hi everyone. Today we're going to talk about a problem where you're given a pyramid. This is a pyramid here of numbers, and you're asked to find a path starting from the top of the pyramid to the base of the pyramid. So there are multiple paths. If you think about it, there are multiple paths from the top to the base. This is the base here, and say for example, this is one path. It can go this way, this way, this way. So you sum of the values, you get 20, I'm sorry, you get 30. So that's one path. You can have another path. You go to 13, you can go to 8, you can come down to minus 22. So there are multiple paths. If you think about it, there are big of 2 to the power of n paths. So you would have to evaluate each of these paths and do the max across all of them to come up with the max path. And that is what constitutes approach 1, which is the brute force. And obviously this does not scale as n grows. So just a quick note. So this is not necessarily a binary tree. The reason being that you can have multiple paths to a element at the base. So for instance, in this case, you have a path from 15, 14, 16, and then to 1. You can also have a path from through 2 to minus 1. This is unlike the binary tree setup where a leaf is not shared by multiple nodes in a binary tree. So just an observation, does not necessarily change the approach. The solution we talk about here applies to binary trees as well. Let's talk about a second approach. So so if you look at how the pyramid is composed. Like I was saying, it's very much akin to what a binary tree looks like. So if you were, in a way, somehow, if you were able to compute the solution on our subproblem, which is the pyramids that are are rooted at the children of, say, 15. So if you, for instance, if you're able to compute the max path for the pyramid that's rooted at 14, as well as the pyramid that's rooted at 13, then the question is there a way to leverage those solutions to those subproblems to compute the solution of the original problem? And it appears to be the case. For instance, if we have a value here, if you have a value here, let's call the max subpath rooted at the pyramid starts at 14 as, say, v1, and correspondingly the value of the pyramid that rooted at 13. What you could do is you could do a max of these two, and you could add it to the 15, which is the value at the top of the pyramid, to give you the max path of the max, or to give you the sum of the path through the pyramid from the top to the bottom. That gives you the maximum value. So this lends itself to a recursive way of solving the problem. Let's come up with a function. Let's call it max path. Again, this is just pseudocode. Let's say I have a class called node, and I'm taking in an object, call it node as well. And let's say the node has the following properties. It's got the left, it's got a right, and it's got a value. Okay, so left means it's a pointer, or it's a reference to the node that's to the left of the current node, and similarly the right, and the value is the value that's in that node. So you could say, since you're formulating this as recursion, let's think about the base case. The base case is where if you have a situation where you're your node is null. Say for example, if you get down here, then you gotta just return 0. Right, so if node is equal to null, then you just return 0. Otherwise, what you could do is you return node.value plus the max of the solution to the subproblem on the left pyramid of this node and the right pyramid. And there you go. There you have it. That's your simple recursive solution. Now note that the time complexity here is again big of 2 to the power of n, because you're essentially you're touching each and every node in the pyramid and going through every path possible. And what you're also doing here is you're, say for example, if you look at this pyramid, it's a common pyramid in both the left and the right pyramids of 15. So you're recomputing the values there, right? So that's in no way good. So if there is a way to add a wrinkle to this solution for approach 2, it would be intuitively if there is a way to avoid recomputing, say the value of the solution to this pyramid. There are multiple such pyramids. If you're able to cache the solution and compute it once and cache it, and then reuse this cache value for subsequent references to this pyramid, then you can get some optimization there. So that leads us to approach 3, where you leverage some sort of memoization or caching with approach 2, and you can get a better time complexity. So the time complexity in this case is, the worst case you can do is basically you're going down the height of the tree. You would be doing that for each node. So you could say big log into the base 2 is the best you could do if you do this caching. So that's it, folks. Hope you enjoyed this problem, and thanks for listening.